Hey everyone, in this video we are going to talk about regressions, which are a method for analyzing continuous variable. And so specifically, a regression analysis is the way to evaluate the relationship between some kind of quantitative response variable and one or more continuous explanatory variables. And mostly here we're just going to focus on what's called a simple regression, which is where we're dealing with a single explanatory variable and a single response variable. So in this video, I will walk through some of the fundamental concepts associated with regression analysis. Then we will review how to calculate a regression in R, and then we'll wrap up with a more extensive example based on some of my research in ants. So to start out, we're just going to focus on that situation with two continuous variables. So for thinking about this, we'll start out thinking about an example for studying ages of lions. So knowing how old lions are is really important for understanding population dynamics for a population of lions. So that'll tell you if lions are of a reproductive age, how susceptible they are to dying, all kinds of things. But it's really hard to keep track of an entire population of lions to know the precise age of every single lion that's within the population that you're interested in. So there's a lot of motivation to come up with other methods to estimate how old lions are. So one other thing that researchers have found is that for lions where they do know how old the lion is, so for example, lions from a zoo population, as those lions age, they start to have more black pigment on their noses. So what that means is that nose color could be a really useful indicator of age that's a lot easier to measure rather than tracking lion ages in the wild, without getting eaten. So for addressing this question and for addressing other questions of this nature, the first step is always to plot your two continuous variables. So here on my x-axis, I've got the proportion of a lion's nose that is black, and then on the y-axis, I've got how old that lion is in years. And so if we just look at this visually, we can kind of see a pattern, right? So younger lions have less black noses, and then older lions have noses that have proportionally more black on them. But the question is, how do we describe this pattern quantitatively? And the solution for doing this is one that you've probably already practiced in other contexts, which is to define a line that fits these data. And I'm going to designate this using the equation that's shown here. So we can think of our y variable, so age in years, as being related to some kind of intercept term, so here symbolized beta naught, and then on some kind of slope function of x. So here my slope term is beta 1. So for any proportion of black nose, I could, if I have a slope and an intercept that I can calculate, I could calculate and estimate how old the lion is. But that doesn't actually tell you how that good fitting line is calculated. What's the correct line for these data? There's a lot of different possible options. So that brings us to kind of our three main questions that we're going to think about with a regression analysis. So this first question is, how do we actually come up with a good fitting line? The next question is this line a reasonable summary of the relationship between the variables that are of interest? And then the third question, which is related to that second question, is that relationship strong enough such that we can use that relationship for prediction? And that's a distinct question from number 2. So I want you to think about each of those components a little bit differently. And I think the reasons why will become more clear as we work through some of these examples. Okay, so here's the method that statisticians have come up with for figuring out the good fitting line. The method is called least squares regression. And what this method involves is finding a line where there's the smallest possible distance of that line from all of the points in a data set. So to give you a sense of this, here I've got 3 different graphs with lines, and I want you to take a moment to scrutinize these and see which one you think represents a least squares line, so smallest possible distance from all the points in the data set. And once you've had a chance to do that, I'll show you what I think. It's this third one. Okay, but mathematically, how is that really accomplished? So here's how that is accomplished or calculated. So this is, Q here is a least squares calculation. So what this is doing is this is saying for each individual value of y, so for example, the value of y that's up here, how different is this value of y from what I would predict based on x, right? So this is just a rearrangement of the equation that's up here. So if y is very different from what I would predict, right? So here's my actual y, but my predicted y is going to fall right here along this line, right? So if my actual y is very different from my x, then this value is going to be large. And by convention, we take the square of this value in part to account for, y's that are either bigger than or smaller than what's predicted. For calculating the least squares, we would repeat this type of calculation for every single data point, and then see, if we adjust the position of this line, where do we get a value of q that is as small as possible? And that is our least squares line. And actually doing this calculation either involves doing a bunch of calculus or it involves a ton of trial and error number crunching. So most people don't actually do this process by hand anymore. And instead, we can rely on R to do this calculation for us. And so if you use R for a regression analysis, then the outcome that you will get will be an estimate for each of these values, for your intercept value and for your slope value, and then also a range, which is basically equivalent to a standard error measurement for each of these values. So our estimate is indicated here by the solid line, and I've indicated the range around that estimate with this gray shaded area. And we don't need to get too bogged down in the range right now, but be aware that that's incorporated in regression analysis. So that's how we come up with a good fitting line, just through the methods of least squares. So the next question then is this line a reasonable summary of the relationship between these two variables? So that's going to involve some statistical evaluation of the slope and the intercept estimates. So very much like for other statistical analyses, we're going to conduct some statistical hypothesis testing for both the slope term, beta 1, and also for the intercept, beta 0. And so as with other types of statistical calculations, we can kind of split this up into a null statistical hypothesis and an alternative statistical hypothesis. So the null statistical hypothesis is that beta 1 is equal to 0. The slope is equal to 0. So what this is saying is, regardless of how black a lion's nose is, we're going to get an equivalent age, right? Whereas the alternative is that beta 1's not equal to 0, so it's significantly different from 0. So in that case, that could indicate that either there's a positive relationship, such as is shown for lion noses and age, or it could indicate that there is a negative relationship between these characteristics, so it's just not equal to 0. And there's a similar statistical hypothesis test for the intercept term as well. In general, we probably won't be particularly interested in the intercept term, but I will show you an exception to this at the end of this video. But the type of statistical test is very much equivalent for the intercept. So the null hypothesis is that the intercept is 0, and the alternative is that the intercept is not equal to 0. So we have to do a statistical evaluation to determine whether or not that line is a reasonable summary of the relationship between the two variables. And so we do this statistical test with a type of t-test where the degrees of freedom in this case are equal to n minus 2. And again, we're not going to get too bogged down in the details for that, but I'm going to show you in R how that statistical test gets calculated. So then that statistical test then is addressing the second question of, is that line a reasonable summary of the relationship between the variables of interest? But there's another question that we can address with a regression analysis, which is this question of, is that relationship strong enough such that we could use that relationship to make a prediction? So for our lions, for example, can we go out and take a picture of a lion, quantify how black the lion's nose is, and be able to estimate how old that lion is? And so the method for doing this, for evaluating the strength of the relationship between two variables, is to use a value called the R-squared value. And so this R-squared value basically tells us for a given x, how well can we predict y? And actually the inverse is also the case. It will also tell us for if we knew y, how well we could predict x. And so R-squared typically value ranges between 0 and 1. So an R-squared that's close to 1 indicates that we have very good predictive power. So we know if a lion's nose is exactly 60% black, exactly how old it is. And in contrast, if our R-squared is small, so if it's really close to 0, that means we have relatively low predictive power. So if we know how black the lion's nose is, we don't really know exactly how old it is. We have a pretty large ballpark for that. So for this particular example, the R-squared value is actually 0.61. So, how would you interpret that R-squared value? So just to kind of reiterate the point here, I'd say it means we have a 61% predictive power for predicting a lion's age based on its nose color, or vice versa, predicting its nose color based on its age. But we can also keep in mind that we have a 39% chance of being wrong. So for example, if we have a lion with a nose that's about 75% black, notice that we have some lions that are much younger and some lions that are a lot older than what we would predict based on that nose color. So there is some room for error with an R-squared of 0.61. So let's just test this idea out. So with these two plots I'm showing you here, which of these do you think is going to have a higher R-squared value and why? And if you said the plot on the left, you'd be correct, right? So in this case, the points are all much closer to the line. So we'll have a more accurate prediction of y based on any given x, or vice versa here, compared to in the plot on the right, where we won't be able to predict y as accurately for a given x. So I think people are often tempted to read a lot into an R-squared value, but there's some really important limitations to the R-squared value that you should keep in mind when you're evaluating it for a given plot. So here I'm drawing out two different types of plots, and these plots are really interesting in that the plot on the left has a fairly high R-squared value, so it's close to the value for the lions I showed you a moment ago, right? So this R-squared value is 0.63. And then in contrast, On the plot on the right, I've got a very, very low r-squared value of 0.09. And I've got the question here of, did I do this right? So, here I've got very contrasting r-squared values. Is this a good reflection of the relationship illustrated between x and y? And I'm hoping that you can see, just from evaluating a plot of these data, that the answer in both cases is no. So what's happened here is, yes, most of the points would line up with a linear relationship, but above a certain threshold number, this relationship changes. So that suggests that maybe a linear fit is not the best way to describe the relationship between x and y here. And that's in spite of having a reasonably high r-squared value. And the same is very much true over here in the right-hand plot as well. And actually, if we fit a function like a quadratic function here, I think we discover that that function would be a much better fit for these data. So that would allow us to much more accurately predict y for a given value of x. And if we fit a quadratic function, we'd probably wind up with an r-squared value that's much higher than the r-squared for the linear fit here. And so this also, I think, really emphasizes the importance of plotting your data before you charge ahead with your statistical analysis, because often visually we can tell that there's something else going on with data that we might not detect if we're just looking at a bunch of numbers. And there's one other caveat that I haven't illustrated here, but it is that just because you have a small r-squared value, that does not mean that an x and a y are unrelated to each other. So what can happen is there may be a relationship between your x and your y, and it may be a significant relationship, but there could be a lot of other factors that are also contributing to a particular measurement of your y variable. And this tends to be very true, especially for ecological data. Ecosystems, and for a lot of ecological questions, they tend to be influenced by a very wide range of factors simultaneously, and it's often very difficult to pinpoint every single factor that's producing a particular outcome. And so as a result, there may be a lot of variation that's present that's not necessarily accounted for by an x variable. And yet, even so, there may still be a significant relationship between that x variable and some y variable that's being measured. So don't put all of your emphasis on an r-squared value if you're conducting a regression analysis, but also think about the other question at hand, which is, is there a significant relationship between these variables? And this also gets me to just illustrating that there are other types of regressions that exist. And again, this helps show why you should always start by plotting your data. So here, this just shows a range of other types of functional relationships that can occur between an x variable and a y variable. So, it could be something like a negative exponential relationship, a sigmoidal relationship, or a relationship that has some kind of asymptote somewhere. But in fitting each of these lines to each of these collections of points, that same basic principle of least squares still applies. So we're looking for a line where the difference between the points, each individual point in the line, is minimized. Okay, so that's really a lot of the details for regression analysis. So next we're going to shift over to RStudio to work on calculating regressions in R. All right, so for this example, we're going to work with the orange tree data again. And what we're going to examine is whether there's a connection between a tree's age and that tree's circumference. So I'm going to load in the orange tree data, and I'm going to comment my code data. So just using the data step for orange, and then check it using the head function. Okay, so this just shows me the first 6 lines. So I've got multiple trees and trees at different ages, and then the circumference of those trees. And again, the first thing you want to do is plot your data before you conduct any analysis. So I'm just going to use the plot function, and I'm going to put circumference on the y-axis, and then I'm going to put age on the x-axis. I'm going to run that plot function before I add anything fancy to it. Okay, and that runs fine. So now I can go back and make it more beautiful by making it orange. This PCH argument changes the shape of the points to filled circles. And then I'll add in a nicer x-axis label, age in days, and a nicer y-axis label, circumference. I don't actually know the units for the circumference, but I should include those if I'm being complete with this example. Okay, so I've made that plot, and what you can see is it looks like this might be fit fairly well with a linear relationship. So let's go ahead and calculate that linear regression. So what I'm going to do is I'm going to create a new object that I'm going to call orange LM, and you'll see why I'm putting this analysis into a new object in a moment. So I'm just going to use the LM function for linear model. And again, I'm interested in the relationship between an orange tree's circumference and how old it is. And I'll use the data step to tell R to look within the orange data frame. So if I run that, you'll notice I don't see any output right away on the command line. And if I just call up that object directly, orange LM, that doesn't spit out very helpful information. So it does tell me about the formula that's in play, and then it's got estimates for the intercept and the age, but nothing else. So if I want to examine the statistical output for a linear regression, what I need to do instead is use the summary function to examine the output for that orange LM model. So here I've got oodles of information about this regression analysis. We're going to skip over the part of this that refers to residuals, and instead we're going to look at the part for coefficients. So what we see here are a column with estimates for the intercept, so 17.4, and then for slope, so as a function of age, so the estimate for slope is 0.107. And there are standard error terms associated with those estimates, as you can see here. And then next to that, we've got statistics that will tell us, are these relationships significantly different from 0? So what you can see here is the t-statistic for the intercept is 2.02, and my p-value is 0.052, so it is not significantly different from 0. And then in contrast, for age, my t-statistic is 12.9 and my p-value is very, very small. So the slope of this relationship is statistically significantly different from 0. So it's significantly positive in this case. So for every increment in age, there's an increment in the circumference of 0.1. Couple other pieces of information here. So this also will note my degrees of freedom. So I've got 33 degrees of freedom, so associated with each of these t-statistics. And then this output also reports my adjusted r-squared value. So in this case, my r-squared value is 0.83. So that's a fairly good fit between a tree's age and the tree's circumference. So I have fairly high predictive power for telling how big a tree is based on how old it is, or vice versa. And so then once I've calculated those statistics, I can actually also annotate my plot with that relationship. So let's do that in a separate section here. Oops, up in the script. So take the plot with the regression line. If the regression was not significant, then I would not annotate the plot with this line. So I'm going to just copy and paste my plot function here, and then I will add to that an AB line function. And this is where having put that linear regression model into an object is really helpful. I can just put that into my AB line function and boom, it plots it on the plot. And then I'm also going to annotate this particular plot with some text. So at x position 350, y position 200. And so I'm going to add on the r squared value. So r squared was 0.83. And then this /n inserts a line break. So below that, I'm going to add in p is less than 0.0001. All right, so if I run that, that just annotates directly onto my plot. And that's it for regression analysis in R. So now we'll go back over to our last step. Okay, so just briefly about other types of regressions. If you do find yourself in a nonlinear regression situation, come and get help from myself or from Dr. Burke. Oftentimes we can actually use a data transformation to make a linear regression work. So hopefully you remember from an earlier lecture video me showing you this non-normally distributed data for the population density of counties in the Midwest, right? So this is a skewed distribution, but there I showed you that if I took the log base 10 of these values, then I got something that looks approximately like a normal distribution. So by doing that, that would actually put these data onto a linear scale. So I could analyze them using a linear regression. And so similar tricks can apply to other types of data. All right, so now I'm going to conclude with an example from some of my own research. So this is a paper that I'm actually in the process of writing right now. And so for this project, what I did is I went out and I collected ant queens while the ant queens were running around on the ground looking for a place to start a new nest. And that can be a very energetically intensive activity. So I had a couple of questions about that process of starting a new nest. So the first question I had is just, is there a relationship between how big the ant queen is and how much energy she burns? So I'm really interested in the relationship between two continuous variables, the queen's body mass and her metabolic rate. And as with the lion example, one of those is a lot easier to measure than the other. It's much easier to weigh queens than it is to measure their metabolic rates. And then I had a second question as well, which is there an energetic advantage to pairing up with another queen to start a nest together? So you can kind of imagine this could go a couple of different ways, right? So the queens might cooperate with each other and there might be some energy savings associated with pairing up. Or it could be that if you put two queens together, they start to fight with each other. So it could be energetically costly, or it could also be energetically neutral. So we needed to collect data to find out. So here are data from this project. So my x-axis is a queen's body mass, and as I noted, I have log transformed these axes to make the data behave in a linear fashion. Same thing here on the y-axis. This is a queen's metabolic rate, log transformed, and there are two types of points here. So the solid points are for queens by themselves, and then the open diamonds are the metabolic rate for a queen that is in a pair. And it might look like a bit of a constellation, but there's something going on here. So first, we're going to look at the slopes and R-squared values for single and paired queens. So after a regression analysis, I found that for single queens, this relationship had a slope of 0.58 plus or minus 0.2, and obtained an R-squared value of 0.53. And then for paired queens, I got a slope of 0.85 plus or minus 0.23 and an R-squared of 0.48. So these R-squared values are a little lower than what we saw for the lion regression, but they're still a fairly high measure of goodness of fit. So there's still a fair amount of predictive power of a queen's metabolic rate if we know her body mass. There is a fair amount of variation here, though, even so. So that's probably a product of the fact that an individual's metabolic rate is a product of a lot of different interacting factors, but body mass can explain a substantial amount of the variation in a queen's metabolic rate. But if I statistically compare the slopes for queens by themselves or queens in pairs, I actually find that the slopes are very similar to each other. They're not different from each other. So the nature of the relationship is the same for single versus paired queens. However, one thing that I did find was that in this case, the intercepts were different, as indicated by the higher elevation of the line for queens by themselves. So what this means is, regardless of how big a queen is, there is a metabolic advantage to starting a nest with a friend. So hopefully that's a fun example of regression analysis. And with this video, hopefully you have the tools you need to conduct regression analyses for your projects.